This is chapter 2 homework. Um, it's really not so much circuits yet as it is about resistance, power, um, some things with current and so forth. So this is my version of the homework. This is the picture. See here, it said all wires are made of the same material, lengths were the same, and so forth. So if you look at this picture for number 5, the current would split for the left side and the right side and then come back together at the bottom. So therefore I1 and I4 must be the same. I3 and I2 would actually be half as much as 1 and 4 because the current would be evenly split in this case. For number 9, this is a little bit different because it's thinking about electron current. So we've got a positive and a negative here. So an electron would actually travel counterclockwise. In other words, it would be pushed out of the negative and go toward the positive. So the potential energy here would decrease. Essentially, energy always flows from higher to lower, if you can. And so therefore here, this electron is at high energy. It's going to do something out here, maybe heat up the wire. When it's done, that energy has been converted from electrical potential energy to something else. Again, probably heat. If there was a bulb here, it would be light. So that energy loss actually goes to the microscopic collisions with the electron and the atoms in the wire. And the chapter actually talked a pretty decent amount about that. The analogy that I always like to give is imagine like a pinball machine. Think about things bouncing around there. That does take energy because you can hear the sound, you can see the things bouncing off. Or you could think of a freshman trying to get down a crowded hallway. Actually, you trying to get down a crowded hallway of freshmen who are moving in random directions. You kind of bump off of them, slows you down. So for letter D, inside the battery, the electron would move down. So it would move actually from the positive to the negative. You might think that's a little odd, but in the battery, essentially the chemical energy causes a charge escalator, and there's a picture of that in the textbook, which causes the negative charge to gain energy again. So in a complete circuit, remember, charge is conserved. It's not that charge is used up. So if it flows counterclockwise outside the battery, it has to flow from top to bottom inside the battery. So inside the battery, the electrical potential energy will increase. The chemical potential energy stored in the lead acid paste will decrease. For number 10, this is asking you to rank resistance. So we would think about the resistivity formula, which is a constant rho multiplied by the length divided by the area. Well, they only give you radius, so you have to really think about the area as being related to the square of the radius. So for number 1, it's 1 unit of length for me and 1 unit of radius. So I did 1 over 1 squared, and that's 1 unit of resistance. Again, it's not a real number, but it's something I can use for comparison. For number 2, it's the same length, but twice the radius. But because the area is what matters here, it'd be 1 over 2 squared, which is 1/4. So if this had 1 ohm, this wire would have, that is not right. Let me think about that. Oh, the length, no, sorry, the length is 1, the radius is double. That's correct. I don't know why this looked weird to me. So it'd have 1/4 of the resistance. 3, similar things, except in this case, both the length and the radius are doubled. That's half the resistance of this. And again, these aren't real numbers. Maybe wire 1 would have had 7 ohms. If that's true, wire 3 would have 1/2 of that, or 3.5 ohms. Continuing with that, I got 2 for number 4 and 1 for number 1, so this is my ranking. 4 is greater than 5 is equal to 1, is greater than 3 is greater than 2. Number 15 was asking about the current going through each of these. It's simply a ratio of voltage to resistance. This is similar to the lab we did with Ohm's law. 16 is looking at the electrical potential, and that was bad. I didn't label that as volts. Maybe I can do that now. Hold on. Volts. I don't know why it's green. Maybe change that. Perhaps to nice blue. Okay, so that goes over here. As you pass through each of these dry cells, you gain potential. So at point F, I guess it was 0 here, 0 volts was defined, and then you go through 1 EMF, 2 EMFs, 3 EMFs. So it's a little like a charge escalator. And then between C and D, assuming it's an ideal wire, no change. Across the resistor, as you go from D to E, you go back all the way down to 0. And then from E to F, stays at 0. Number 22. We were looking here to see which one bulb had the most current going through it. It gave you the power and the voltage of each. And you could use essentially the power formula, P equals V times I, rearrange it to get the current. For number 24, correct answer was C. I've got an explanation there. For number 29, the answer was also C. So if you have questions about those, let me know. Hopefully the screencast proved useful.